Good morning, students. Today we will discuss about the topic magnetic field at any point on the axis of the current carrying coil. Meaning we have need to find out the what is the value of the magnetic field, ठीक है, at any point on the axis of the circular coil. So for this purpose, first of all, we have need to consider a circular coil that carry the current. So let us consider this is a type of a circular coil. Let us consider a circular coil is placed perpendicular to the plane of the paper. Okay, my point. This coil is not like this. Okay, this coil is kept like this. Okay, it is not kept on the plane of the paper. Okay, so we have need to consider. Let us consider a current carrying coil placed. This is the plane of the paper. This is the plane of the blackboard. So let us consider a coil is placed perpendicular to the plane of paper. This is a plane of paper, plane of blackboard, and you are keeping the current carrying coil perpendicular to this plane of paper. So always keep in mind this is the back side of this coil, this surface, and solid means represent this side of the coil. So first of all, you have required that where the means axis of this coil. This is the axis of the coil. So first of all, we have required that the point, that point we have need to find out the magnetic field intensity. So consider the current is flowing through this coil is, ठीक है, anti-clockwise direction. Meaning current is flowing through this coil in this manner. Okay. So by the use of White-Seiberg law, you have required that what is the value of the magnetic field at here. So first of all, for this purpose, we will take any current element on the surface of this coil. ठीक है, so we have taken the means any current element on the surface of the coil A, B, and the direction of the DL is you know very well that is always perpendicular to the, ठीक है, so always you will draw the direction of the current elements, ठीक है, by making the tangent on this coil. So I told you the current is flowing through this coil is anti-clockwise. So you have taken the current element at here and here. This is the current element you have chosen on the surface of the coil. What is the direction of the current element that you have taken the current element AB? The direction of the AB is coming in which side? Outward side. So the direction of the current element is this side. And suppose we have need to find out the magnetic field intensity at point P, then what is the distance from this current element point to this point? Suppose that is S. That is S. And the radius of this coil is A, and from the center of the coil and the point P distance is X. ठीक है जी? And this point P, so this line AP, so this point from here to here, and this axis makes an angle is suppose phi here. Okay, my point. So see here, we are having the coil, okay, and the coil is kept perpendicular to the plane of the paper. So if we keep it perpendicular to the plane of the paper, then what is the direction of the current element? This is coil and the current is flowing anti-clockwise. We have taken the element at here. So the direction of the means current element on this coil is like this. Understood? Clear? And the direction of the means current element is this side. And we have need to find out the magnetic field intensity at point this. So keep see here. This is a current element direction. And suppose, ठीक है, that distance you have taken from the coil at this point. At this point, you will need to find out the magnetic field intensity. Suppose that the current element direction is this side, and the point there you need to find out the magnetic field intensity is this. So the direction of the displacement vector, ठीक है, and current elements makes an angle here 90 degree. But always keep in mind, see here, if I will do like this, ठीक है, what is the angle between the current element and this displacement vector is 90 degree. If I will do like this, what is the angle between the current element and displacement vector? 90 degree. So the whether you will change the position, whether you will change, ठीक है, the direction of the displacement vector, the means angle between the current element and this displacement vector is always a 90 degree. See here, what is the angle? 90 degree. What is the angle? 90 degree. Okay, but the angle between this and radius of this coil is goes on changing, because radius will come this side and this line is this side, displacement vector. So the angle between the radius of the coil and displacement vector will change, but the angle between the, ठीक है, current element and the displacement vector is not changed. So if we will do like this, then the angle is 90 degree. If I will make like this, then the angle is also, you will observe that what is the angle between this current element and this 90 degree. So see here, current element direction is outer side, outward, and this I have taken, ठीक है, the point P here. So ठीक है, displacement direction is this side, but the angle between them is 90 degree. So ठीक है, the value of the magnetic field due to this current element AB, ठीक है, at this point is according to White-Simon law, dV is equal to mu naught by 4 pi I dl sin 90 degree by s square. At here, at P, due to current element, the value of magnetic field is this only. Okay. Now the point is how this magnetic field acts here. What is the direction of the magnetic field at here? See here, this is the current element direction, this is displacement direction, distance of the means point P from the means element is this. If you want to find out what is the direction of the magnetic field, then you know very well that you will use the Maxwell screw rule. So also you know very well that the direction of the magnetic field is always perpendicular to current element and also perpendicular to displacement vector. Clear? So suppose if I will take this, then see here, this is the direction of the means current element, this is the direction of the displacement vector. Okay, so where you will keep the screw? You will keep the screw at here. Okay, and how you have need to rotate the screw? So this is, see here, screw is perpendicular to this also, and screw is perpendicular to current element also. So how will you rotate the screw? From current element to this side. If I will rotate the this screw from current element to displacement vector side, then the main screw is moving this side in the plane of the paper. In the plane of the paper and this side, this is plane of paper, blackboard, in the plane of the blackboard, and it is where? It is perpendicular, ठीक है, to the axis. Okay, my point? If I will take like this, but here you will see this is the direction of the magnetic field, and if you rotate the main screw from here to here, then it means the direction is coming this side. In the direction, ठीक है, that is perpendicular to this also, perpendicular to this also, and direction of dV is perpendicular to both, and it is in the plane of the paper this side, upper side. Okay, above the means we can say that this axis. So see here, but the line is not, displacement vector is not like this. If see here, current element to this way, displacement vector, if suppose displacement vector is just like this side, then what is the direction of the magnetic field is coming? Direction of the magnetic field at point P is coming, okay, in this sense. Okay, but this side, if this displacement vector is perpendicular to this current element, then the direction of the magnetic field will come like this. But the displacement direction means, see here, change. So if I will change this in this manner, then the direction of the magnetic field is also changed, and it will come like this. And in the direction means if the magnetic field is coming in the plane of the paper this side. So dV is coming towards this side. So this is the magnetic field direction due to this current element at point of P. Now dV means divided into how many components? One is this and one is this. Okay, meaning this is dV and this is also dV. What factor? See here now how do we find out that this horizontal component of magnetic field and which component is vertical. If see here, this means axis line makes an angle. Okay, with this part of the magnetic field is 90 degree, and this means displacement vector, the distance from the point P, distance of point P from the current element line, this. Okay, then this dV is also perpendicular. So on this line, this is perpendicular, and on this line, this is perpendicular. And angle between these two lines is phi. If the angle between these two lines is phi, so angle between these two perpendicular on this line and on this line is also same. So resultant magnetic field makes an angle with, always you know that with horizontal. So it will become dV cos of phi, and here it will become a dV sin of phi. Understood this? Okay, now see here. If I can take the current element here, now any current element CD I will take at the downside. So what is the direction now? What is the direction of the current element? It is the outer part of this loop, and this is the dotted inner part. So direction of the current element is sine out. The direction of the current element is this way. Okay, and the displacement vector direction is in this way. Okay, clear? But the angle between them is 90 degree, you will see. So the in this way also. In this way, so direction of the magnetic field required at this point. So it will come like this. Screw I will keep here. Okay, so where to where I will need to move the screw. From where to where I have need to rotate the screw, because this is also means front element direction. This is displacement vector from here to here. So direction of magnetic field at point P due to this is coming perpendicular to this also, to this also. So how the means magnetic field will come? In this way. It is perpendicular to this also, it is perpendicular to front element also. So how will you rotate the screw? See here, from front element to displacement vector. So in this way, front element here and displacement vector here. So how will you rotate the pen? See here, I have to rotate the pen from here to this side. So pen is coming, direction of the magnetic field is coming in the plane of blackboard. Okay, and perpendicular to displacement vector also, and this way also. So the direction of the displacement vector is coming perpendicular to both. But see here, if in this way means angle between the displacement vector and current element is 90 degree and displacement vector is like this, then direction of magnetic field is coming like this. But here if you will see, then the displacement vector like this, but direction of the displacement vector is like this. So what happens? This means magnetic field direction is also changed, means we can say that in this sense. Okay, so the direction of the magnetic field due to this current element that carry the current, okay, inward side. So the direction of the magnetic field is appearing here, means this way. Okay, the distance from here to here you know very well, that is also S7. So the magnetic field is produced by this is also dV, because distance same है, area radius same है, current same है, so dV value is also same है. So this dV dash is also divided into two parts, dV dash cos of phi and here dV dash sin of phi. ठीक है? Okay, this is the means we can say that diagram है here.